In this lesson video, we're going to start trying to understand how we can get power from coal, oil, wind, water, nuclear power even. It's all done using magnets, specifically changing magnetic fields. Here's a magnet and a coil of copper wire. Remember, copper is not magnetic. The coil has a light bulb attached to it, but no battery, no power supply. The magnet over here, though, does have a field, so let's show the magnetic field as well. If I wiggle the magnet a little, you can see the field moving too, changing its pattern. Now, if I move the magnet towards the coil, look what happened there. The light came on for a moment. I'll try again. Oh, the light came on when I took the magnet away as well. But if I just leave the magnet next to the coil, nothing. The light bulb is only lit whilst the magnet is moving. That kind of makes sense, otherwise we'd be getting free energy. The chemical potential energy in my body is transforming into kinetic energy in the magnet, which is transforming into electrical energy in the circuit, and then heat and light in the bulb. That is electromagnetic induction. The moving magnet, or rather, the changing magnetic field, has induced an EMF and hence a current in the coil. Can I make the bulb stay lit? Like permanently? How would I do that? Well, you probably thought that I could just keep the magnet moving, but that's going to get boring fast. Here's a solution. As the magnet spins, its field moves around, so the magnetic field changes all the time, so the EMF is induced all the time. We can use water to do this, and in fact that's how dams work. We could also use wind or steam. But I'll come back to that another time. How can I increase the size of the EMF? Give me 3 factors. Well, pause if you don't have any, but speed and strength of the magnet are 2. What else? Well, the number of turns in the coil is important as well, as we can see here. At A level, we talk about flux linkage. The field lines are also called flux lines, and the important thing is how quickly the total number of field lines inside the coil changes. If the magnet moves faster, the change is faster. If the field is stronger, the amount of change from 0 to maximum is bigger. If there are twice as many turns in the coil, there is twice as much linking as the field is linked in each turn. A simpler way to consider it is that EMF is induced when a field line moves across a wire. So, key ideas are stronger magnetic field means more EMF. Faster movement means more EMF. More turns means more EMF. And this is Faraday's law. If you find that tricky, that's okay, it is hard, but it is important as well to try to get to understand it. So pause, go back, look at some other sources, read textbooks, but we've still got some other tricky bits to look at. So, moving on. Which direction is the current? Well, we need Lenz's law for this. The direction of the induced current is such that it opposes the change producing it. That was Lenz's law. Think about that. The direction of the induced current is such that it opposes the change producing it. Back to my first demo. I was moving a magnet towards the coil and inducing an EMF. Lenz's law means that the EMF is going to oppose that. It's going to try to stop the magnet approaching the coil. How is that even possible? What I mean is, can you think of a physics way that a coil of wire can stop a moving magnet? How does a coil stop a moving magnet? Well, back to electromagnets. If I ran a current through the coil, like so, I will generate a field that has a north at this end and a south at this end. Like poles repel, so the coil will try to push the magnet away. It is opposing the motion of the magnet. I'm moving the magnet in, it tries to push it away. So it is opposing the change that produces it. If the magnet stops, the EMF stops, so the electromagnet dies away. Pulling the magnet out, the EMF will now try to stop the magnet moving away. So it wants a south pole at this end. This means the current flows the opposite way. We can see that as I move the magnet towards, then away, the induced EMF is switching directions. So in this lesson, we've covered electromagnetic induction, the amazing area of physics that allows us to convert movement into electricity. What we're going to do in the next couple of lessons is see how we can then channel that through building generators.